All right, in this video, we're going to go over the work, power, and energy notes for physics. So first up, what is energy? Energy is the ability for something to cause change. It's the capacity to do work, and we'll talk about what work is towards the end of the PowerPoint. Right? There are various forms of energy, such as potential, kinetic energy, thermal energy, electrical energy, chemical energy, sound, and nuclear energy, as well as a few others. We're only going to focus on a couple of these, so don't worry. When we talk about unit and measuring energy, it's going to be measured in joules, and it's abbreviated with a capital J. So first type of energy we're going to talk about is kinetic energy. Kinetic energy is the energy a moving object has because of its motion. So if an object is moving, then it has kinetic energy. The amount of kinetic energy the object has is going to depend on two things. It's going to depend on the mass of the object as well as the speed of the object, or really technically speed, velocity, all right? Because in your formula, you're going to see those two variables. You're going to see mass and velocity. So your formula is kinetic energy equals 1/2 times mass times velocity squared. You may see this formula written like this with KE here, or you also may just see it abbreviated with a K instead of KE, but it's the same thing. Right? So our first example here is how much kinetic energy does a jogger have if his mass is 60 kilograms and he's moving at a velocity of 3 meters per second. So we're going to take our kinetic energy formula and we're going to plug in what we know. So we've got our mass of 60 and our velocity of 3. So we end up plugging in 1/2 times 60 times 3 squared. Then we can type that in the calculator and get 270 joules. Right. Next up is potential energy. Potential energy is the stored energy an object has, and there's a few different types of potential energy, and we're going to go over 3 of them. The first type is elastic potential energy. This is stored energy that something has that can stretch or compress. So like a rubber band or a spring, you can stretch them or compress them, and they have elastic potential energy because of that. So think of like if you stretch a rubber band just a little bit versus stretching it a lot, it's got a different amount of elastic potential energy based on that. Right. The next type is chemical potential energy. This is energy stored in chemical bonds. It's what a lot of your chemistry class is based around. Examples include both food and gasoline. For food, your body breaks down the food, breaks down those chemical bonds, and releases that chemical potential energy to use and converts it to other type of energy. Same with gasoline. Your car burns it and converts it to other types of energy. Then the last one we're going to talk about, and the main type of potential energy we're going to deal with, is gravitational potential energy. So gravitational potential energy is in stored objects due to their position above the Earth's surface. It'll depend on the mass and the height above the ground. And an example would be just an item on top of a bookshelf. Any item on Earth is going to have gravitational potential energy, and the higher it is off the ground, the more it's going to have. So the formula for this is your potential energy equals your mass times gravity, which is 9.8, times your height. So you will see this formula either written PE for potential energy, or you may see it with GPE for gravitational potential energy, but it's the same thing, right? So let's go over our example. How much potential energy does a 50 kilogram object have when it is 4.2 meters above the ground? So we're going to take our formula and we're going to plug in what we know. So we know our mass is 50 kilograms, we know our height is 4.2, and we know G is 9.8. So we're going to multiply 50 times 9.8 times 4.2. So this one's pretty straightforward. All you got to do is multiply. So when you type that in your calculator, you'll get 2,058 joules. All right, moving on to the law of conservation of energy. The law of conservation of energy states that energy cannot be created or destroyed. Energy can change from one form to another, but the total amount of energy is never going to change. And it brings us to our next formula, which can look really intimidating to most students, but I promise you it's not. So this really long formula is actually only made up of the 2 previous formulas. We have MGHI, which the I stands for initial, so initial height. This is your potential energy formula. Plus 1/2 mass times VI squared. This is your kinetic energy formula. We just did both those formulas. Then it equals your potential energy formula again, plus your kinetic formula again. So what it is your initial potential and kinetic energy together is going to equal the total at the end. All right. That's not too scary when you break it down, but let's do an example of solving, because what you're going to end up solving for on a quiz or a test when using this formula is one of these individual variables. Normally it's the final height or the final velocity, but you might also be asked to solve for the initial velocity or the initial height. So we've got we're asked to calculate the velocity of the roller coaster that it has at the top of the second hill. So here's our diagram. The second hill is this here where it's labeled S. That's what we're looking for, the velocity there. So the speed on the velocity on the first hill is 30 meters per second, and the mass of the car is 100 kilograms. We're given the heights in the diagram of 50 meters and 25 meters. So we're going to plug everything in that we know. So I highly encourage you to write down this when you're solving these problems. Don't just start typing things in the calculator, because it's really easy just to flip numbers around and get the wrong answer by accident. So our mass is 100 times 9.8 times our height of the first hill is our initial height is 50. So that's for our first part. Then plus 1/2 times our mass again of 100 times the initial velocity on the first hill is 30 squared equals the mass of 100 times 9.8 times the height of the second hill, which is 25 that we get from the diagram, plus 1/2 times the mass of 100 times final velocity squared, which that's what we're solving for. All right, make sure you leave that letter in there. Don't just leave it blank, because then you're going to get confused later. Leave the VF squared in your work. All right. So now my next step is going to be to simplify this down, because right now this is a lot of numbers to work with. So let's take each of the 4 sections and simplify them down in the calculator. So I'm going to type in 100 times 9.8 times 50. That's going to give me 49,000. And I'm going to type in separately 1/2 times 100 times 30 squared. I'm going to get 45,000 for that. Then I'm going to type in 100 times 9.8 times 25, and that's going to simplify down into 24,500. And then 100 times 1/2 is just 50, so I get 50 via VF squared. So that's a lot less scarier and a lot less numbers to work with. So now my next step is going to be simplified again. Let's go ahead and add this left-hand side together. That's going to give us 94,000 on the left equals 24,500 plus 50 VF squared. Now we can subtract this 24,500 over to the other side. That's going to give us 69,500 equals 50 VF squared. Then the next step, we want to divide this 50 over, giving us 1390 equals VF squared. And we don't want VF squared. We want just VF. So the last step is 2 square root, and we get 37.3 meters per second as our final velocity. All right. So that's not too bad, but we'll do a few more practice problems throughout the unit before we get to your test. All right. Moving on to mechanical energy. Mechanical energy is the total amount of potential and kinetic energy in a system, and it can be expressed by this equation. Mechanical energy equals your potential plus your kinetic energy, or simply put, ME equals PE plus KE. It's energy due to a position and the motion of an object, right? So how much mechanical energy does a roller coaster car have if its kinetic energy is 50 joules and its potential energy is 100 joules? Right? Formula is really easy, like the easiest one we've ever worked with. You're just going to add the 2 numbers together and get 150 joules, right? But you typically won't see word problems like this solving for mechanical energy. Instead, you're going to see problems like this, where it's either like a skate park or a roller coaster diagram or something similar to that, where you're asked for mechanical energy in the diagram, but you're also solving for things like potential and kinetic or velocity and well. So what this question is just asking you to find all of the missing information for this skater whose mass is 60 kilograms. And we're going to find all the missing pieces. We're only going to work with 3 formulas, though. We're going to work with that mechanical energy formula. We're going to work with the potential energy formula and the kinetic energy formula. So 3 pretty easy formulas to deal with to find all of this information. So it does take a while to work out problems like this, but they're not really that hard, right? So let's work through this. So it says the 60 kilogram skater starts at the bottom of the ramp and goes 8 meters per second. So let's start with spot 1. Let's find his potential energy, because we know his height is on the ground here. So whenever the object's on the ground, whether it's a skater or something else, it's going to be a height of 0. So 60 times 9.8 times 0 is just 0 joules. So now I can write that in my list of 0 joules. All right. Next up, I can find his kinetic energy. 1/2 times mass of 60 times 8 squared. That 8 did come from up here in our directions. And when I multiply that on the calculator, I get 1,920 joules. All right, so that's my kinetic energy for spot 1. Now for mechanical energy, simply just going to use that mechanical energy formula and add them together. 0 plus 1920. I don't even really have to write this down. It's just going to be 1920, right? Joules for the mechanical energy. Now, here's the thing to remember with these kind of questions. Once you find the mechanical energy at one spot, it's going to be the same for all the other spots. So this has 3 spots in it. If it had 5, 10, 20, doesn't matter. For this skater, his mechanical energy total is always going to be 1,920 joules. So I can go ahead and label that on the other 2 spots as well. So here at spot 2, my mechanical energy is 1,920 joules. And at spot 3, it's 1,920 joules. Okay, so now that's filled in for all 3 spots. All right, let's move on to spot 2. For spot 2, I am given his height here in the diagram, but I'm not given the velocity. So let's start with what we know, what we can work with that we know first. So since I know the height, I'm going to go ahead and find potential energy, because potential energy formula has height in it. So it's going to be 60 times 9.8 times 1. That's going to equal 882 joules. Right? Now for kinetic energy, I would normally just use the kinetic energy formula, but I don't know velocity yet. So the other way to figure it out is use that mechanical energy formula, and I can plug in the mechanical energy because I know that is 1,920. I know my potential energy is 882, and then I can subtract it to get my kinetic energy. So when I subtract 1920 minus 882, I'm going to get 1,038 joules for my kinetic energy. Now I can solve for velocity using my kinetic energy formula. So I'm going to plug in that 1,038 for the kinetic energy equals 1/2 times the mass of 60 times the velocity squared. I'm going to simplify this 1/2 and this 60. That's going to give me a 30. And then I'm going to divide that over the other side, and it equals 34.6 equals your velocity squared. We don't want velocity squared, we just want velocity. So we're going to square root it to get 5.9 meters per second. And that's going to go in my chart here. Okay. All right. Last spot 3, we are given the velocity at 0 because he's going all the way up to the top. This is right before he's like all the way up and he's about to start rolling back down. So his velocity is 0 at this one brief little moment, but we don't know the height. So to start off with, we're going to go ahead and figure out what the kinetic energy is, which is going to be 0, because if the velocity is 0, when we multiply it out, our kinetic energy is going to be 0. All right, so I'm going to add that to my list. And then for potential energy, since I have 0 kinetic, all of my mechanical energy has to be my potential energy. So it's going to, your potential energy is going to be 1,920 joules. All right. Now to find my height, I'm going to use my potential energy formula to solve for height, because that's the only formula that we're working with right now that has height in it. So potential energy equals mass times gravity times height. So 1,920 equals 60 times 9.8 times my height. So I'm going to divide 60 times 9.8 and then divide it over to the other side, and I'm going to get a height of 3.3 meters. All right. So I know, again, this is a lot of work. We will keep doing examples and practice problems as we go through the unit, but just remember that you're only using these 3 formulas, okay, to work everything out. All right, let's move on. So next up is work. In physics, work is defined as a force acting upon an object that causes a displacement, or basically it's a force causing something to move, right? The object has to move in order for work to be done, and that force has to be what causes the movement. If a force is applied to an object, but it's not what's making it move, then that's not work being done on it, all right? So like this lady here, she's pulling on this box with a rope at this angle, and the box moves from over here to there, right? But these 2 gentlemen are just pushing on a wall, and no work's being done there because they're not moving that wall anywhere. All right, so let's do some examples. For number 1, a student applies a force to a wall and just becomes exhausted from pushing on a wall. I hope you're thinking that no work is being done on this wall because the wall's not moving anywhere despite the force being applied. For number 2, a calculator falls off a table and free falls to the ground. Is there work being done? Think about whether a force is being applied and whether that force is causing the object to move. So, of course, if it's fallen to the ground, there is movement going on. And there is also a force being applied. Gravity is what's causing it to fall and is pulling it to the ground. So work is being done. All right, number 3, a waiter carries a tray full of beverages above his head by one arm and walks across the room. So there's a force being applied to hold on to that tray, and they are moving across the room with the waiter as he walks across the room, but there's actually no work being done on the tray here. He's just applying a force to hold it, and it basically becomes like an extension of himself because the force being applied to move him across the room isn't the same force that's being applied to hold onto the tray. So there's not actually work being done on the tray, right? Then the last one, a rocket accelerates through space. This one is more obvious. Work is being done because the engines are pushing it across space for it to go, all right? So the formula for work is going to be force times distance times cosine of our angle. So work and energy are going to have the same unit. It's measured in joules. And when work's done on a system, that system's change in energy is equal to the amount of work done on it. So we do have our formula written as work equals FD times cos of our angle. F is the force, which is measured in newtons. D is for displacement, or distance is going to be measured in meters. And then you have your angle between the force and displacement. So here, like that lady that was pulling the box, her force went up this way. We only care about the horizontal part here because this object or this box is moving horizontally across. We don't care about how much of the force is being applied upward on the object. All right, so let's go through an example. How much work is being done on a vacuum cleaner if it's pulled 3 meters by a force of 50 newtons at an angle of 30 degrees above the horizontal? So we take our formula, we're going to plug in what we know, which is 50 newtons times 3 meters times cosine of 30 degrees. Type it all in the calculator, you're going to get 130 joules. All right. You might also see sometimes some problems where an angle is not given, but it'll say instead direction, that the force is applied in the direction of motion. So this one's how much work is being done by pushing a car 2 meters by a force of 40 newtons in the direction of motion. This means that the direction isn't parallel to the direction. The direction and force are parallel to each other. They're both going the same way. So there's no angle. The angle is 0. So you can still plug everything in. Your force of 40 times 2 meters times cosine of 0, because again, your angle is going to be 0. Cosine of 0 equals 1. It does not equal 0. So just make sure you type it in so you don't screw it up by saying your answer is 0. So in this case, it's going to equal 80 joules. And again, the angle is 0 because the force is applied in the direction of motion. When you see that phrase, your angle is 0. All right. Moving on to the very last thing for this set of notes is power, and it's probably one of the easiest things in these notes. Power is the rate at which work is done. It is a work-time ratio. The unit for power is in watts, just like you think of when you think of light bulbs, right? And it's just work divided by time. So it's a really easy formula too. We won't use it really too much. But what is the power? How much power is used if the work is 500 joules for 15 seconds? We're going to divide just 500 by 15. That gives us 33.3, and then our units is watts. So not too bad there, right? But that is it for this set of notes. Of course, as always, if you have questions, please let me know, and I'll be happy to help.